All right, so very good afternoon, and we'll continue our discussions on signals and systems, right? Now, in the last session, we had seen how you could interconnect several ideas of signals and systems, particularly the impulse response, the step response, right? The response of a system to an input obtained by convolution with the impulse response, and the response to the same system by looking at it as an RC circuit with a voltage divider, right. So, all these ideas could be interconnected when we, so see, in fact, we saw that we saw how you could think of the output input relationship, right. For example, we saw that you could arrive at the same conclusion. You could arrive at a conclusion of what would happen when a phasor is applied to an RC circuit, looking at it from the point of view of the impulse response, and you could come to the same conclusion by looking at it as an RC circuit and doing a voltage divider principle, right? And they match. That's so this kind of interconnection. Why I brought those out is that this kind of interconnection needs to be emphasized when you're teaching such a course, right? As teachers of the subject, it's very important to bring these interconnections, bring these relationships, right, between what you study in circuits or what you study in network theory and what you study in signals and systems. They're all related. In fact, what I recommend is, in the sessions that you're going to do with my teaching associates, I would expect you to design such problems. So, you must design a few more such problems which teach you how to connect circuits, signals, think of circuits as systems, think of them from the point of view of circuit analysis and come to the same conclusions through the impulse response and so on. Right? Now, we'd like to go further. We'd like to look further at how you would analyze. Now, we were talking about the analysis of a system for all time, right? But suppose you wish to confine yourself to a function over a limited time. So, you want to look at a function x of t, right, over a limited time. How would you do it? So, let me put down what I want to do in this session first. So, xt looked at for limited time. Then, should you be using the Fourier transform, or should you instead use only a part of the Fourier transform, right? Should you use only certain frequencies? So, should we use only certain frequencies? Should we confine ourselves to discrete frequencies? Okay, that's one thing. The second thing is, what we did in the morning was to see what happens to one phasor, right? But now take the whole input in general, right? You obtain the output by convolving the input with the impulse response. What does this do in the Fourier domain? Can you look at the whole thing in the Fourier domain? If the input and the impulse response have a Fourier transform. So, all functions don't have a Fourier transform. We must also appreciate this, right? So, we have to restrict ourselves to functions that have a Fourier transform. But if a function is limited in time, then you can work with what is called its Fourier series, because you can then make a periodic repetition and then confine yourself to one period, right? But if you're working with the Fourier transform, then you are limited in the scope of functions that you can deal with, because all functions don't have a Fourier transform. But where a function has a Fourier transform, and where the impulse response also has a Fourier transform, if the impulse response has a Fourier transform, it means the system has a frequency response. All systems don't have a frequency response. If a system is unstable, it would, in principle, you're not guaranteed that it will have a frequency response. There are unstable systems which have a frequency. That's a bit of a tricky marginal case. But even so, you're not guaranteed. And therefore, you need to look at them a little bit askance, a little bit carefully. Anyway, so let's say, the Fourier domain is equivalent Fourier domain effect of convolution. Okay. And the third thing that we want to understand is sampling. Sampling a sinusoid and therefore sampling the signal. What are the implications of this? If you sample a sinusoid, what happens? What happens to sinusoid? And if you sample a signal, if you think of the signal as comprised of several sinusoids, what is the consequence? Right? These are three things that we now like to address. Right? So let's begin with the second one first, because that continues from what we were doing in the morning. And then we'll take up the other two afterwards. You see, let's take the Fourier transform and let's look at it from a slightly different perspective. We said, yes, of course, that the Fourier transform, h j omega of the impulse response is the dot product. So it's like a dot product of the impulse response with this phasor, right? Now, we can also use this idea to reconstruct ht from its Fourier transform. So suppose, for example, I tell you that a two-dimensional vector has a component of 5 along the first orthogonal direction and 3 along the other orthogonal direction. How would you reconstruct the vector? You would multiply the component along one orthogonal direction by a unit vector along that direction, isn't it? So you would say 5 u1 cap plus 3 u2 cap, okay? And you can keep doing this for as many dimensions that it has. Multiply the component by a unit vector in that direction and add all such components. That's how you reconstruct the vector from its components, right? Now you can generalize that idea to the Fourier transform. So this is a component along e raised to the power j omega naught, right? So how will you reconstruct ht from its components? Multiply the component along by the vector, and then here you are going to integrate over all the components. Now what is it that indexes the components here? Each frequency gives you a different component. So instead of integrating on time, now you need to integrate over frequency, right? So, and now this frequency also runs from minus to plus infinity, right? This frequency also runs from minus to plus infinity. Why do we have, see, now this is another, this is a point, this is a stumbling block for a lot of students. What is it that forces you to deal with both positive and negative frequencies? See, a lot of times students have this confusion. In fact, many instructors also have a confusion why we should be dealing with negative frequencies. So, there is a tendency to believe that positive frequencies are meaningful, but negative frequencies do not have a meaning. Now, if you take a minute to think, in fact, let me ask you this question. I would like you to think again. This time, let's do some kind of thinking, and between yourselves. How would you answer this question? Suppose a student asks you, why should I deal with negative frequencies? It's only positive frequencies that have a meaning. So, okay. But before, so I'll repeat what you people are saying. So, some of you saying that, one of you said that, it's as if you have the other frequency 180 degrees out of phase. Some of you said that, it's ease of analysis, right? And, well, my question is, is there something, now you need to take a minute to think, whose frequency are we referring to here? And then you will be able to answer this question. Whose frequency, whose angular frequency are we referring to here? Are we referring to the frequency of a sinusoid, or are we referring to the frequency of something else? Angular frequency of something else. We are referring to the angular frequency of a sinusoid. So if it's the angular frequency of a sinusoid, then of course we have to agree that only positive frequencies make sense. But in the Fourier transform, are we talking about the angular frequency of a sinusoid, or are we talking about the angular frequency of something else? So we need to look carefully at what we are doing. Yes? Anything. No, but here in the Fourier transform, whose angular frequency are we looking at? Okay, I'm hearing various answers. There's a truncated sinusoid, there's an impulse, there is frequency of signal. But what did you apply to the system when you derived the Fourier transform? What did you apply to the linear shift invariant system? Yes, a phasor. So whose angular frequency are we looking at? It's the angular frequency of the phasor. What is a phasor? A phasor is a rotating complex number. The phasor is not really the same thing as a sinusoid. In fact, a sinusoid has two phasors embedded, right? One phasor rotates counterclockwise and one phasor rotates clockwise. So any sinusoid actually has two equal and opposite frequencies creating it. So in that sense, there's nothing sacrosanct about positive frequency either. Positive frequency only means, now here in the Fourier transform, the way we've written it, positive frequency only means counterclockwise phasor rotation. And therefore, for every counterclockwise phasor rotation, you need a clockwise phasor rotation to make a sinusoid, right? So, so we tend to have this affinity for the positive frequency and a dislike for the negative frequency, which comes from our confusion with the frequency of a sinusoid. But actually in the Fourier transform, we are not talking about the frequency of a sinusoid. We are talking about the frequency of the phasor. So this point is a finer, so these are finer points that one must be aware of when one wants to clarify them to the student. Is that right? So anyway, that's why my integral here runs from minus to plus infinity and not from 0 to infinity, right? So I'm just emphasizing, but these are typical questions that need to be answered. Now, of course, to take care of the scaling, because you want a unit vector, you may need a constant. It turns out that constant is 1 by 2 pi. So you can reconstruct h of t from its Fourier transform by this, and this has a geometric interpretation, a physical interpretation. You're multiplying the component by the vector along the direction of the component, and you're integrating over all such components. You're bringing together all such components. Component multiplied by unit vector integrated over all the components, right? So this is the inverse Fourier transform. Yeah. Now, you see, let's look back at what we were doing for convolution, as we said. You see, The whole purpose of going into the Fourier domain is also to ease the process of convolution, right? So, I can think of xt in terms of its inverse Fourier transform. So, any xt applied, provided, of course, we will assume right now that we are talking about signals and impulse responses and outputs, all of which have a Fourier transform. As I said, that may not. To be clear, let's take an example of a signal which does not have a Fourier transform. Suppose you take a growing exponential. Does it have a Fourier transform? Well, what if it did, what would the Fourier transform be? It would be e raised to the power 2t, e raised to the power minus j omega t dt integrated from 0 to infinity, because there's a ut there, right? Now, is this integral convergent for any omega? No. This integral does not converge for any omega at all. This integral diverges for all omega. And therefore, this signal has no Fourier transform, right? So, that's why I'm just trying to emphasize why we need to say that you are confining yourself. You're not looking at all possible signals. The convolution relationship is most general for a linear shift invariant system. But this, what we are doing now in the Fourier domain, restricts itself to those signals where, and those systems or those situations where all the signals involved have a Fourier transform, right? Alright. Now, suppose you have a linear shift invariant system. With an impulse response of ht, and you give it the input xt. Let's write xt in terms of its Fourier transform from here. 1 by 2 pi integral minus to plus infinity x j omega naught e raised to the power j omega naught t omega naught. And we wish to find out the output. Let's invoke the principles of superposition as it would be for the linear shift invariant system. So, let's take what happens when we apply one particular e raised to the power j omega naught t. So, you apply e raised to the power j omega naught t to a system what emerges? H j omega naught times e raised to the power j omega naught, right? We saw this. If you multiply this, x of j omega naught is a constant. It's a complex constant. It's a constant. So, you're multiplying e raised to the power j omega naught t by x of j omega naught. What would emerge now because of linearity? X j omega naught times this. And now if I integrate, now when I integrate with respect to all omega, effectively I am invoking the principle of additivity here, right? So, when I integrate, integration is the limiting case of addition, right? So, when I integrate over all omega here, and of course divide by 2 pi, that's just a constant, I would effectively get 1 by 2 pi integral over all omega naught okay. You agree with me? So, you have invoked the principle of linearity and you have invoked the principle, well in fact I have invoked linearity, right. Here shift invariance has already been invoked when I looked at what happens to one phasor. So, their shift invariance has already been invoked. So, I am not explicitly invoking shift invariance again, right. Now, look at this carefully. Does this look like an inverse Fourier transform? Yes, it does. Inverse Fourier transform of what? Of this product. Is that right? So, this is effectively the inverse Fourier transform of the product. Is that right? Does everybody appreciate this? Right? So, what are we saying in effect? I have given the inverse Fourier transform of xj omega naught, which is the input xt, and what I have received at the output is the inverse Fourier transform of the product xj omega naught into hj omega naught, which means the output Fourier transform must be the product. Is that right? The output Fourier transform, which means the output Fourier transform must be the product. In fact, this also has a simple physical meaning. So, the output yt has the Fourier transform given by the product. Okay. So, what does it mean? When I convolve two signals, their Fourier transforms are multiplied. That is what it indicates, right. I have convolved xt with yt, xt with ht to get yt, right. So, xt gets convolved with ht to get yt, and y of j omega is equal to x of j omega into h of j omega. In fact, let us take a minute to appreciate what we are saying here. What are we saying here? The component of the output along the angular frequency omega naught is equal to the component of the input along angular frequency omega naught multiplied by the component of the impulse response along the angular frequency omega naught. So, it is a component wise decoupling. It is a component wise decoupling. Each component of the output can be calculated with the corresponding component of the input. This is another way to understand this product relationship. Each component of the output, each angular frequency component of the output, each phasor component of the output can be obtained in a decoupled manner from all the other angular frequency components. So, there is a certain sense of orthogonality, a certain sense of being perpendicular. Now, this is an advanced idea. Let us not get too carried away by it for the moment. There is a certain sense of perpendicularity. See, when do things get decoupled? When there is a certain sense of orthogonality about them, right? When do signals behave in a decoupled manner? When there is an orthogonality between those signals, when the signals are perpendicular to one another in some sense, right? The sense of being perpendicular here. But let us not get too deep into that. Let us not get too worked up what the mathematics behind that perpendicularity or orthogonality. But you must appreciate that the idea is coming. Is that clear? The idea is coming forward here. The idea of being perpendicular. Okay. Anyway, but this interpretation should be well appreciated. See, many of us, when you study signals and systems, or when you teach signals and systems, it's, people often know that convolution in the time domain implies multiplication in the Fourier domain. What I am trying to stress here is the various interpretations of it. It's not enough to give a mathematical derivation, it's always a good idea also to give interpretations, right? What does this product principle mean, right? What implications does the product principle have, right? And if these are well appreciated, then the idea that the output Fourier transform must be the product of the input Fourier transform and the Fourier transform of the impulse response has a very simple and neat interpretation, has a very appealing meaning, and that should be appreciated. So I hope this meaning has been appreciated, right? All right. Now we take up the first question that we had raised there. Namely, if I wish to deal with a signal over a limited part of the time axis, right? What can I do? Do I need the whole Fourier transform, or can I take only a part of the Fourier transform? So let's answer that question. Well, let's assume, without loss of generality again, this idea of without loss of generality. Again, as teachers, we have to appreciate what this without loss of generality means. Let's take a minute to reflect. I want, if you want, discuss among yourself. And I'd like you to volunteer to tell me what is the meaning of this perpetual statement which we keep uttering once in a while, without loss of generality. What does it really mean? I would like some of you to volunteer to come and explain to me. Why do we keep saying without loss of generality once in a while? Anyway, let me tell you what I am saying without loss of generality here. I am saying without loss of generality, let us consider a signal to lie between 0 and t. Now, why am I saying without loss of generality? Abstraction. Abstraction in what sense? When I say without loss of generality, I really mean that even though I am taking a particular case, it does not affect the general analysis, right? The same thing can be very trivially carried to any general situation. That's what without loss of generality means. So, to understand or to make my analysis neater to present, I choose a particular case. But then choosing that particular case does not affect the general analysis. That's what without loss of generality means. Now, here I take a signal lying between 0 and t, but the signal could have as well lain between within any other interval of t, the analysis would not change. That's what it means, right? So, anyway, let's take the signal to lie between 0 and t, and now now the point is you are not interested in what the signal does outside this range, right? So, you don't care. The signal may be present or may be completely absent, that means the signal may be completely 0 outside the range, or whatever it is, you don't care. You can put anything you like outside that range and analyze the signal in this range. In such a situation, one very simple and neat thing you can do is to periodically repeat the signal, right? So since we are interested only between 0 and t, one may periodically repeat the signal over every interval, every successive interval of t. So what you are doing from 0 to t can be repeated from t to 2t, from 2t to 3t, and so on, and from minus t to t, and so on and so forth, right? So whatever you have here is brought here, is brought here, is brought here, and so on, right? And we are all the time interested only in what is between 0 and t. So we don't mind doing this. Now if we don't mind doing this, do we have to deal with the whole Fourier transform, or can we deal only with some discrete points of the Fourier transform? In fact, now, if you've made a periodic signal, you could think of the signal as a combination not of all possible sine waves or not of all possible complex exponentials with all possible angular frequencies. you can think of it as a combination only of those angular frequencies which have this period. Is that right? So, so instead of trying to reconstruct, which means, in this case, when you were trying to reconstruct initially in the inverse Fourier transform, how do you reconstruct the signal? You said, I multiply the component by the unit vector in the direction of the component and sum over all such components or integrate over all such components. Now I am saying, I don't need to take all the angular frequencies, all the phasors with all possible angular frequencies. I need to consider only those angular frequencies which have multiples or submultiples of this period, which means the frequencies which are multiples of 1 by t. So we need only consider angular frequencies omega naught which are multiples of t, m times 2 pi by t, m integer. Okay. So, since you're see now remember, when you're doing this, you're again focusing on the signal only between 0 and t, right? So, you ask yourself, how would I take a dot product? You see, earlier you were taking a dot product by thinking of the signal as lying on the entire time axis. Now I take a dot product only on the 0 to t. So what would that dot product be? So dot product as restricted to 0 to t is integral xt e raised to the power j and only those frequencies. You're not considering all frequencies, right? So j m 2 pi by t times t, okay, omega naught t, alright, dt, but integrated only from 0 to t. And we take the complex conjugate of this as before. You remember why we took the complex conjugate? Because we wanted the inner product of the vector with itself to be a magnitude squared, right? So is this clear now? This is a new kind of dot product. You're restricting the interval only between 0 and t, right? So this is the component, yeah, this is the component, let's call it the mth component of xt. It's the dot product between xt and this phasor with angular frequency 2 pi by t times m, the mth harmonic, so to speak. But m can have both positive and negative integer values, right? So what is this mth component? It is integral 0 to t xt e raised to the power minus, because it's a complex conjugate, okay. Now, let us investigate one very interesting property of these phasors, this restricted class of phasors that we have. Here the phasors are all in multiples of angular frequencies which are multiples of 2 pi by t. Is that right? So let's take a dot product between two of them in this sense of the dot product. In this sense of the dot product, let us take the dot product of two such components, two such phasors, okay. So you have e raised to the power j 2 pi by t times m1 t and e raised to the power j 2 pi by t times m2 t complex conjugate dt integrated from 0 to t. So I am looking at the dot product of two such in this sense of restricting it to 0 to t. Right? What would this dot product be? Let us see. It is in fact 0 to t e raised to the power j 2 pi by t times m1 minus m2 t dt, which is e raised to the power j 2 pi by t times m1 minus m2 t divided by 2 pi by t times j 2 pi by t times m1 minus m2 from 0 to t, provided m1 not equal to m2. Okay. So you know how to integrate e raised to the power alpha t dt, isn't it? E raised to the power, the indefinite integral is e raised to the power alpha t by alpha, provided of course alpha is not 0. If alpha is 0, then there's an integrating of the integration of a constant. So if m1 minus m2 is 0, then this integral becomes simply t. Okay. Now what is this integral? You have e raised to the power j 2 pi m1 minus m2 t. You substitute t equal to capital T and substitute t equal to 0. How much is this integral? You see, e raised to the power, so it will be e raised to the power j 2 pi m1 minus m2, right? How much is this for m1 not equal to m2? E raised to the power j 2 pi times an integer, right? 1. E raised to the power j 2 pi times an integer is 1. So this is equal to 1. And of course, when t is equal to 0, it's 1 anyway. And the denominator is non-zero. So you have a 1 minus 1. In fact, this is not surprising. What you are doing here is to integrate. See, when you take such a dot product of two phasors, both of which have a multiple of this angular frequency 2 pi by t, then that dot product itself is a phasor. You know, the dot product itself is the rotation of a phasor on an integral number of cycles. And the rotation of a phasor on an integral number of cycles brings you back to the same point. So therefore the difference is 0. Is that right? So what it means is that the dot product is 0 when m1 is not equal to m2, but it's non-zero only when m1 equal to m2, right? So this, what do you mean when you have two vectors whose dot product is 0? What is the geometry of the situation? The two vectors are perpendicular, right? It's only when the two vectors are perpendicular. That means all these angular frequencies, all these phasors are perpendicular to one another, right? So when you restrict your attention to a certain interval of time, you are talking about a perpendicular set of vectors. You are talking about a perpendicular set of vectors. Is that right? So now it's very easy to reconstruct xt from its orthogonal components. So reconstruction. Suppose you have a number of perpendicular components and I tell you the component of the vector in each of these directions, right? How will you reconstruct the vector? It's very easy. Multiply each component by the orthogonal unit vector in each direction and add these up, right? So how would you do it here? Now remember, when you took the dot product of the vector with itself here, when m1 is equal to m2, it's the dot product of the vector with itself. That gave you t. So t is the dot product of the vector with itself, right? So when you take the dot product of a vector with itself, it gives you the squared magnitude. Is that right? The magnitude squared of the vector, right? V dot v is the magnitude of v squared, okay? So the magnitude of each of these vectors squared is t. So, if I want to normalize the vector, that means make it unit norm, unit magnitude, what should you do? Divide by square root of t, because t is the square of the magnitude. But then, dividing by square root of t is inconvenient. So, what we do is, on the forward side, you see, we should have divided by square root of t here if you wanted to take the dot product with a unit vector, right? Instead of doing that, we don't divide by the square root of t here, right? We should have divided by the square root of t here, and we should have also divided by the square root of t when reconstructing. But we take both those square roots of t on the reconstruction side. Okay, so we say the reconstruction of xt from its components would be essentially 1 by square root t multiplied by 1 by square root t times, well, the mth component, whatever you call it, what you want, multiplied by a unit vector there. Right? Pi by m t, and now here, you see, you should have, now you don't integrate here because you have only a discrete set, isn't it? You sum overall in. Because now you have a discrete set. Alright? And this gives you 1 by t times sum overall. You can call the mth component of xt, let's call it xm, right? E raised to the power j 2 pi by t times mt. Now, of course, the same thing could be done the other way. So, you have brought the 1 by t here, but you can also bring the 1 by t there. In fact, most of the time that is what is done. So, instead of bringing the 1 by t here, you could bring the 1 by t here, right? So, either way is all right. You bring the 1 by, whatever it is, you need to account for this, unit magnitude business, right? Anyway, so this tells you how you could decompose a signal which is to be seen only on a limited interval, right, into its Fourier components. In fact, what we are writing here is called a Fourier series. It's called the Fourier series. So, this is the Fourier series expansion of xt, which is valid only either in two situations. Either you are dealing with a signal only on a limited interval of time, from 0 to t, right, or you are dealing with a periodic signal actually. Either way, in both cases, you could talk about a Fourier series. Otherwise, you need to talk about a Fourier transform, right, because all the frequencies are required to reconstruct the signal from its components. Is that right? All right. Now, let's take up the third question that we were trying to address. Namely, what happens when you sample the sinusoid, right? What happens when you take only samples of a sinusoid? What ambiguity does it bring? Or what do you lose in the process? You see, I'm talking about sampling a sinusoid. I could have talked about sampling a phasor, right? I'm talking about sampling a sinusoid because the sinusoid seems to be closer to our appreciation of what happens in reality, right? We don't really see phasors in reality. But then, whatever analysis I'm doing here for sampling a sinusoid will also be easily carried to sampling a phasor. Anyway, so suppose you had a sinusoid. This is the third question that we were trying to address, isn't it? So let's say you have a sinusoid. You have an xt which is described by a naught cos omega naught t plus phi naught. Now instead of describing the signal at each time, let's take only samples of the signal at all multiples of some time interval. So let's say take samples t equal to, say, let's say all multiples n times t0, right? Or rather, let's not, okay, ts is the sampling interval. I'm sure many of you must have heard about the Nyquist principle. Like, how many of you have heard about the Nyquist principle? Nyquist, yes, quite a number of you have heard. How many of you have thought about the Nyquist principle from the point of view of one sine wave? How many of you have thought about the Nyquist principle thinking of one sine wave? Raise your hands. Yes? What have you thought about the Nyquist principle from the point of view of one sine wave?
Have to reconstruct it, and the frequency should be double.
Okay, but that's true. Frequency should be double.
But we have also thought it in a combination of sine waves, because under that we had signals in which we had multiple sine wave components of it. Then we find out what's the maximum frequency there, and the sampling should be double of that maximum frequency.
True, quite true. Now, have you wondered, so of course, and you have an analysis for it, isn't it? You have an analysis why it should be twice the maximum frequency component, aliasing effect. Now, have you thought about what happens to a single sinusoid when there is aliasing? When you sample a sinusoid, what does it do to the sinusoid? You thought about it? Or let's look at it this way. You have this sine wave. Right? And you don't quite keep this sine wave, but you keep very narrow pulses taken at intervals of ts like this. So very good, yeah, it's good attempt. So you don't keep the sine wave, you keep very narrow pulses taken at intervals of ts. Now this train of pulses that you have, it's a non-uniform train of pulses, right? Does it have sine wave components in it? Have you thought about it? Does it have the original sine wave embedded somewhere within it? Does it have many other sine waves embedded within it? Yes, which sine waves? You understand my question? So you had this sine wave, and now you've replaced that sine wave by very narrow pulses taken at multiples of ts, right? Does this train of very narrow pulses spaced by ts also have sine waves in it? Does it have the original sine wave in it? Does it have other sine waves in it? What does it have? Okay, yeah. Why don't you, yeah. Why don't you sit, yeah. Okay, so I have one answer which says that it does not have the original, you feel? So are you saying it doesn't have the original, or it has the original? It doesn't have the original. What else does it have?
Period of ts. Period of small components. Very variations of the sinusoid happens.
It has many sinusoids. Which sinusoids? Of what frequencies? Signal frequency. Which signal? Where is the signal here? The signal was the sinusoid, right? Yeah. So which are those mth components? Which are the mth components? Well, let's first look at an interesting idea about the sinusoid. So let's look at all the samples. Let's ask a different question. Let's ask whether the same samples could have come from some other sine wave. You see, I'm trying to present to you an idea which is, you see, otherwise there's a tendency by using textbooks to straight away start drawing a spectrum, and which is correct. There's nothing wrong with it. But I find students often fear the idea of sampling. They think of sampling as very esoteric. It's not that esoteric, really, if you think about it. You see, take these nth samples. You have x of n ts, right, which you could call as x of n, the nth sample, to be a naught cos omega naught t plus phi naught, with t replaced by nts, isn't it? So nts plus phi naught, right? Now, what is it? To answer the question, which other sine waves could have created the same samples in the same places? How many such sine waves do you have which could create the same samples in the same places? 2n. Which n? No, not twice. You see, what is it that will create the same samples in the same places? The ambiguity in the cosine. What is the ambiguity in the cosine? The ambiguity in the cosine is first a plus minus ambiguity, and the other is adding any multiple of 2 pi. Right? Adding any multiple of 2 pi keeps the cosine as it is. Secondly, adding plus and minus makes the cosine the same. So these are the two ambiguities that you have. So you have 2 pi times k, and you want to bring in sinusoids, so you also want the sampling instant to come in. So I do not only keep an integer for which multiple of 2 pi, but also the instant. 2 pi kn plus minus what you have here inside the bracket. So this is definitely true, isn't it? This is true for all n. Adding any multiple of 2 pi, any integer multiple of 2 pi, and replacing the plus minus retains it to be what it is. You agree with me? Yeah. So this is the ambiguity. This is the ambiguity in the cosine. Now let us rewrite this a little bit. Let's rewrite this by, now omega naught. So you have n anyway. So you see, you want to take nts common here. So nts, and which frequencies? 2 pi will have to be then divided by ts, and k here plus minus omega naught, and then plus minus phi naught. Remember, when you're saying plus minus, if there's a plus here, it must take plus, the minus. It's not all the 4 possibilities. When there's a plus here, it must go with the plus, and there's a minus here, it must go with the minus. Right? This is the situation. Agree with me? What is the interpretation of this? All sinusoids, of course, that's right. So all sinusoids with these frequencies would have produced the same samples at the same points. Right? It's obvious. Now, when we meet at 5:45, right, I would like you to think, what happens when we add all these sinusoids? All these sinusoids with these frequencies. So here, of course, I have taken samples. But if I took the continuous sinusoids, make them continuous. That means replace nts by back with the t with which you started. Right? Suppose you added all these continuous sinusoids with these frequencies. But you have to be careful. You must keep the frequencies and the phases. The frequencies are, of course, 2 pi by ts times k, and you take plus omega naught and minus omega naught. If you're taking plus omega naught, the phase should be plus phi naught. If you're taking minus omega naught, the phase should be minus phi naught. If you were to add all these sinusoids with the same amplitude and these phases, what would you get? So I'd like you to think about this question when we meet again at 5:40. Is that right?